Now see, you have seen composition table with respect to addition, with respect to multiplication. Now we are going to learn two more operations which are new to you. They are addition modulo m and multiplication modulo m. See, this addition modulo m and multiplication modulo n will play an important role in group theory. For example, if you take, see examples we will see afterwards. Now, what is the definition of addition modulo m? Addition modulo m is defined as if a comma b belongs to z, that means they are the integers. M be a fixed positive integer, m is also fixed integer. If r is the remainder obtained when a plus b is divided by m, then we will say that r is addition modulo b. Addition modulo, we will write like this, addition modulo mb is equal to r. The meaning of that is, if a plus b is divided by another integer m, then the remainder, for example, if you take 20 addition modulo 6, 5 here it taken, 20 plus 5 by 6 you have to take, 25 by 6. 6 will be 4 times, if you cancel 6, 24, 25 by 6 if you take, what is the remainder? Remainder is 1. 4 6 are 24, remainder is 1. That 1 will be 20 addition modulo 6, 5 value will be the 1. Is it clear? What is it? If you take two elements a and b, a addition modulo mb means the remainder obtained when a plus b is divided by m. Is it clear? That is the addition modulo m. See here, 2 plus 2 addition modulo 7, 3. That is 5 by 7. When the numerator is less than the denominator, then the addition modulo is denoted by the numerator itself. The value is 5. Okay. Now is it clear? A plus b by m. If a plus b is less than m, a addition modulo mb value will be a plus b. If a plus b is greater than m, then the remainder obtained when divided by m, a plus b is divided by m, the remainder obtained will be addition modulo m. Okay. Now see here, you have seen the example. Now see the multiplication modulo. Now the multiplication modulo is, if AB belongs to Z and P is a fixed integer, the remainder obtained when you divide AB by P. If you divide AB by P, the remainder obtained is called multiplication modulo P, and if it is the numerator is less than P, the value itself will be the remainder. Is it clear? This is the addition modulo and multiplication modulo. See the example here. Prove that the set G is 0, 1, 2, 3, 4 is an abelian group of order 5 with respect to addition modulo 5. Now see, clearly you will get the concept of addition modulo now. Now what is the set given to you? 0, 1, 2, 3, 4. See here, 0, 1, 2, 3, 4. You have taken addition modulo 5. Okay. Now here also left column you have written 0, 1, 2, 3, 4. Is it? Now your operator is addition modulo 5. Now 0 addition modulo 5, 0 is equal to 0 plus 0 by 5. That is, this is not equal to the remainder obtained when 0 plus 0 is divided by 5. Is it? 0 plus 0 is 0. 0 is less than 5. So when the numerator is less than the denominator, the numerator itself will be the modulo value. So here 0. Again 0 addition modulo 5, 1. The remainder obtained when 0 plus 1 is divided by 5. 0 plus 1 is 1. 1 is less than 5. you are not able to divide 1 by 5. Therefore, the definition itself says the numerator will be the value 1. Similarly, 0 plus 2 by 5. 2 is less than 5, 2. 0 plus 3 by 5. 3 is less than 5, 3. 0 plus 4, 4 by 5. 4 is less than 5. So, the modulo definition will be 0, 1, 2, 3, 4. Next to see. 1 plus 0 is 1. 1 by 5. 1 is less than 5. So, you will write 1. 1 plus 1 is 2. 1 plus 1 means 1 addition modulo 5, 1. That means 1 plus 1 by 5. For 2 is less than 5. So, you have to write 2 itself here. Similarly, 1 plus 2, 3 by 5. 1 plus 3, 4 by 5. But coming to here, 1 plus 4, 5 by 5. If 5 by 5 means if you divide 5 with 5, the remainder obtained is 0. Is it? So, this value is 0. Similarly, 2 plus 0 is less than 5, 2. 2 plus 1 less than 5, 3. 2 plus 2, 4 less than 5, 4. Again 2 plus 3, 5. 5 is divided by 5. Now, actually the quotient will be 1, but you are not writing the quotient. Remember that. The remainder 5 by 5, it will cancel 1. The remainder will be 0. So, you are writing here 0. Next here 2 plus 4, 6. 6 by 5. That is 5 cancel 1. The remainder is 1. That 1 you are writing here. Similarly, 3 plus 0, this is 3. 3 plus 1, this is 4. 3 plus 2, 5. 5 by 5, the remainder will be 0. 5 by 5 means don't think it is 1 cancels 1. 1 is the quotient. If you divide 5 with 5, the remainder will be 0. That 0 you have to write here. 3 plus 3, 6. 6 by 5. 5 will cancel once and the remainder will be 1. That 1 you are writing here. 3 plus 4, 7. 7 by 5 cancels one time. Then the remainder is 2. That 2 you are writing. Similarly, 4 plus 0, 4. 4 plus 1, 0. 4 plus 2, 6. 6 by 5, remainder is 1. 4 plus 3, 7. 7 by 5, remainder is 2. 4 plus 4, 8. 8 by 5, remainder is 3. Therefore, 3 you got. Now, you are able to know the table, is it? Now see, observe the table. All the entries 0, 1, 2, 3, 4, 1, 2, 3, 4, 0, 2, 3, 4, 0, 1, 3, 4, 0, 1, 2, 4, 0, 1, 2, 3. All the entries of the body, this is called the body. This is the body of the table. If you observe the body of the table, all the entries belong to the set. Therefore, closure property satisfies. When will you say that closure satisfies? If all the entries of the body is in the set. See, in the first example, you have seen the same set with respect to addition, but closure is not satisfied. Here, closure satisfies. Okay. After that, associativity for granted, take it. After that, you have to find out the identity. Now, if you observe the first row, it is similar to the top row. Similarly, if you observe the second row, it is also similar to the left row. First row is similar to the top row. This first column is similar to the top. So, this is the identity. Verify each row and each column is existing. There exists possessing 1 0. Is it? Each row and each column, there exists 1 0. 0 is the additive identity. Addition modulo, with respect to addition modulo also, 0 will be the identity. Now see, first row 0 is there. First column 0 is there. Second row 0 is there. Second column 0 is there. Third row 0 is there. Third column 0 is there. Fourth row 0 is there. Fourth column 0 is there. Okay. Therefore, there exists an unique identity that you confirmed. After that, you have to find the inverse. Now, in each row, see, underline the identity elements. This is the 0 element. Go to top 0. Go to left 0. 0 is the inverse of 0. Now, coming to second row, underline 0 here. 1 is the inverse of 4. 4 is the inverse of 1. See, are you able to see? 1 is the inverse of 4, 4 is the inverse of 4. Now, similarly here, 2 is underlined here. 2 is the inverse of 3, 3 is the inverse of 2. Similarly here, 3 is the inverse of 2, 2 is the inverse of 3. Underline the identity element, go to the top row and go to the left column, and the head of that row and the head of that column will be inverses to each other. Okay, again here. Now go to the top row 1 and go to the left column 4. 4 is the inverse of 1. That only I have written. See here, 0 is the inverse of 0, 1 is the inverse of 4, 2 is the inverse of 3, 3 is the inverse of 2, 4 is the inverse of 1 from the table. After this, what you have to do? Now you are able to show that closure satisfies, associativity for granted, identity exists, for every element you are able to find out inverse. Now still you want to say it is a commutative group. So whether a commutative property satisfies or not, you have to say. When will you say the commutative property satisfies? Draw the principal diagonal. This is the principal diagonal. Okay. Since it is the principal diagonal, verify the column. See here. 1, 2, 3, 4. 1, 2, 3, 4. 3, 4, 0. 3, 4, 0. 0, 1. 0, 1. 2, 2. That means the elements are placed symmetrically with respect to the principal diagonal. Therefore, commutativity satisfies. I think it is clear how to read the composition table and how to write the composition table with respect to addition modulo. Now is it clear? Okay. Now we will move to the multiplication modulo. See. 1, 2, 3, 4, 5, 6. With respect to multiplication modulo 7, whether it is an abelian group or not, we are verifying using the composition table. Now write 1, 2, 3, 4, 5, 6 in the top row, and in the left column in the same order you have to write. Now see how we are filling the table, body of the table. Now see, first row, first column element. Here first column element is 1, here first row element is 1. 1 into 1 by 7. 1 is less than 7. So the numerator itself will be considered as the remainder. So you are writing it as 1. 1 into 2 by 7. 2 is less than 7. You are writing it as 2. 1 into 3 is less than 7. You are writing it as 3. 1 into 4 is less than 7. You are writing it as 4. 1 into 5 is 5 less than 7. 1 into 6 is less than 7. So you are writing. Similarly, if you take second row and first column, 2 into 1 by 7, 2 is less than 7, so you are writing. 2 into 2, 4, it is less than 7, you are writing as it. 2 into 3, 6, less than 7, you are writing. Now see 2 into 4, 8, 8 is more than 7. So 8 by 7, when you divide 8 with 7, you will get the remainder 1. That one you are writing here. 2 into 5, 10. 10 by 7. 10 by 7 means the value you are not writing here. When you divide 10 with 7, the remainder you are writing here. That is 3. 10 by 7 means remainder is 3. 2 into 6, 12. 12 by 7, the remainder is 5. You are writing here. Similarly, 3 into 1, 3. 3 into 2, 6. 3 into 3, 9. 9 by 7 is remainder is 2. 9 into 4, 12. Remainder is 5. Now 3 into 5, 15. 15 by 7, 2 times 14. The remainder will be 1. Next 3 into 16, 18 by 7. 2 times 14. The remainder is 4. That is 4 you are writing. Similarly, if you fill all these things, you will get these 6 things. Now, if you observe how to read the table, see here. If you observe clearly, all the first row elements, all the second row elements, all the third row elements, all the fourth row elements, all the fifth row elements, all the sixth row elements are belongings. This is the body of the table. In the body of the table, all the entries belong to the given set. Therefore, closure property satisfies. Associativity, you have to take it as for granted. Okay, take it. Then find out the identity. Observe each row. Here is 1, second row 1, third row 1, fourth row 1, fifth row 1, sixth row 1. Each column, first column 1, second column 1, third column 1, fourth column 1, fifth column 1, sixth column 1. All the rows and columns are containing identity element 1. Therefore, there exists an unique identity in the set. That also okay. After that, you have to see the inverse for each element. See, here find out 1. Go to the top row 1 and top left column 1. 1 is the inverse of 1. Now second row, if you take here 1 is there, go to the top 4 and go to the left 2. 2 is the inverse of 4. Similarly 1. 3 is the inverse of 5 and similarly 4 is the inverse of 2. Similarly this 5 is inverse of 3. Similarly 6 is inverse of 6. These are the things I have written. Okay, from the table you are able to find out inverse. After that, whether commutative property satisfies or not, you have to see. Draw the principal diagonal like this. This is the principal diagonal. Okay. Then, if you observe 2, 3, 4, 6 and this is 2, 3, 4, 6. 6, 1, 3, 5, 6, 1, 3, 5. 5, 1, 4, 5, 1, 4. 6, 3, 6, 3, 2, 2. So, the elements are placed symmetrically. Therefore, about the principal diagonal, abelian property satisfies. Therefore, the given set is an abelian group with respect to multiplication modulo 7. I think it is clear. See, we will generalize once. How to read out the composition table? First you have to fill the composition table, and after filling the composition table, what you have to do? You have to verify whether all the entries of the body of the table in the group are not. Then it is in the group, closure property satisfies. Associativity, we will take it as for granted. Then you have to verify whether each column and each row is containing identity or not. If it contains, there exists an unique identity. That you have to confirm. After that, you have to find out the identity element in each row and in block, in which block it is there. From that block, you move to the top row and you move to the left column, and the top row head and the left column head will will be inverses to each other. You have seen 3 examples. No, I think you will get the idea. After that, inverse is there, commutativity. In order to verify the commutative property, you have to draw the principal diagonal. With respect to the principal diagonal, you have to verify whether the elements are placed in symmetric order or not. If they are symmetric, it is an abelian group. Now, is it clear how to verify whether the given finite set is an abelian group or not? I think you got a clear idea about addition modulo, multiplication modulo, and how to rate the properties of abelian group from the composition table. Okay. Now see this is another problem. Show that the set of integers 1, 3, 5, 7 form an abelian group of order with respect to multiplication modulo 8. Now see, 1, 3, 5, 7, they are the prime numbers. Now with respect to multiplication modulo 8, they have taken the table here. 1, 3, 5, 7, 1, 3, 5, 7. You have to remember while writing the table in which order you have filled the top row. In the same order you have to fill the left column also. Okay, write like that. Now 1 into 1 less than 8, 1. 1 into 3 less than 3. 1 into 5 less than 5. 1 into 7 less than 8. So you have taken this is less than 8, less than 8, less than 8, less than 8. Therefore, if the numerator is less than 8, then you will write that term itself as the multiplication modulo value. You see? Now here also 3 into 3, 3 into 1. This is, see here, 3 into 3, 9, 9 by 8. 9 by 8 means one time it cancels and the remainder will be 1. That one I have written here. 3 into 5, 15, 15 by 8. One times it cancels, the remainder will be 7. That 7 we have written. 3 into 7, 21. 21 by 8. 2 8s are 16. The remainder is 5. That I have written. Same 5 into 1 less than 8. So 5. 5 into 3, 15. 15 by 8. 1 times 7. 15 minus 8 is, remainder is 7. 25 by 8. 3 times 24. And 25 minus 24 is 1. Similarly 35. 35 by 8, 4 8s are 32, 3 is the remainder. Similarly, this also you have to remember. Now, this is the body of the table. This is the body of the table. From the body of the table, all the entries are belonging to the set. Therefore, closure satisfies. In each column and each row, you are having 1. See, therefore, there exists unique inverse. Now, see here, the beauty here. The principal diagonal elements are 1, unity, identity element. Therefore, each element is inverse to itself. 1 is the inverse to 1, 3 is the inverse to 3, 5 is the inverse to 5, 7 is the inverse to 7. Why? Because the given elements are prime numbers. From the table, all the axioms of abelian group are satisfied. Because the entries are placed 3, 5, 7, 3, 5, 7, 7, 5, 7, 5, 3, 3. The entries are placed symmetrically along the principal diagonal. Therefore, commutative property satisfies. All the properties of abelian group are satisfied. Therefore, this is an abelian group. Now, see, this is the nice problem with matrix. Now, suppose if you take a set of matrices A, B, C, D, it will form an abelian group. Now, this also using composition table we can say that. Now, let G is equal to A, B, C, D. Matrix multiplication we will take. Now, find out AB and BA. AB is equal to BA means you got AB is equal to B, BA is equal to B. AB is equal to BA means commutative property satisfies. Similarly, AC is equal to CA, AD is equal to DA. All the possible combinations you have taken. BC is equal to CB, BD is equal to DB, CD is equal to DC. You are, in order to verify these things, you can easily verify personally by seeing the video. You can get it. I'll give you the time to observe this 1 minute. Now, BC is equal to D, you got. CB is equal to D, BD is equal to C, DB is equal to C, CD is equal to B, DC is equal to B. All the possible combinations are there. Okay. Now, see the next one. B square is equal to A, C square is equal to A, D square is equal to A, you got. Now, from the composition table, like that you have to verify A, B, C, D you have written, A, B, C, D you have written. What is A, see there? A is, what is given A? 1, 0, 0, 1. It is called as identity matrix. So, it is an identity matrix. See here. From the previous things, you have to A, B, C, D. Now, A into A is A into B is B, A into C is C, A into D is D, because A is the identity matrix. Next, you have seen B into A and A into B is B. So, B square is A, BC is D, BD is C. CA is C, CB is D, C square is A, CD is B. DA is D, DB is C, DC is B, D square is equal to A. Now, to observe this, you calculated the matrix and you have written here with respect to multiplication. If you see the table, see, all the diagonal elements are existing. That means every matrix is inverse to it. Is it or not? They are unity. In the previous example you have seen. Here, all the entries, see, body is this. All the entries are in the group. Therefore, closure satisfies. Matrix multiplication is associative, you know. Now, inverses. From the table, A is the identity in G. From the table, A is the inverse of A, B is the inverse of B, C is the inverse of C, D is the inverse of D. All the elements are possessing inverse. Now, along the principal diagonal, the elements are placed symmetrically. This is BCD, BCD, ADC, DC, DC, B, B. Therefore, abelian property satisfies. Therefore, G is an abelian group. Thank you.